Okay, hello everyone. I welcome you to the second problem solving session of NPTEL course Combinatorics. So let's start. We will be solving few problems from bijective counting and basic counting. So our first problem is, in how many ways we need to find how many ways can a photographer at a wedding arrange 6 people in a row from group of 10 people including bride and groom such that both bride and groom must be together in a picture. So we are asked to arrange 6 people in a row. In a row. Two of them we know. Two so two of them we know they are bride and groom. And four we need to choose from group of 10 people. So any suggestion how we can do it?
We can make one group of bride and groom,
Okay.
and considering one, rest we all can arrange, then into 2 factorial
Oh,
for the
yeah.
bride and groom, they can interchange.
Yes. Yes. Very good. So, like in this also, first, like, so what is the first step? First step is see, we need, so he is right. First step is we need to choose 4 people from eight, choose 4 people from eight people. Because 2 people are already bride and groom and we don't need, so we need to choose 4 from the group of 8 people, which is 10 people minus the bride and groom. And step 2 is considering bride and groom as one unit. Arrange 5 units. And step 3, and so for step 1, and these two steps are independent of each other. So for step 1, how many how many ways can we choose 8 people from 4 people? It is just 8 choose 4. And if we consider bride and groom as one unit, and we have to arrange 6 people. So this bride and groom is one unit, and we have these 4 people, P1, P2, P3, P4. And we need to arrange them. So in how many ways we can arrange? Basically 5 factorial. Because 5 options for the first unit, second, and so on. And now so we have 6 bride and groom as one unit, but we can interchange the bride and groom also. Therefore, we'll also multiply it by 2. This, this, this will count the interchanging of bride and groom. So we see this is the final answer. So is it clear how we?
Yeah, it's clear.
Okay, okay. So now the next question is, we have to count the number of divisors in from the number 25 into 36 into 49 raised to the power 4. So first of all, we'll write this number as a prime factorization. So it is basically 5 square into 6 square into 7 raised to the power 4. But 6 is also not a prime number, so we can further break it down. It is 3 square into 2 square into 7 raised to the power 4. So we have to count the number of divisors. So any divisor, so can anybody tell any divisor of this number, what will it be look like? Any divisor of this, suppose this big number is n, any divisor of n will look like, isn't it? It will look like 5 raised to the power a, 3 raised to the power b, 2 raised to the power c, and 7 raised to the power d. What are the range for a, b, c, d? So A is greater than equal to 0, less than equal to 2. B lies between 0 and 2. C also lies between 0 and 2. And D also lies between 0 and 5. So now it is a simple counting problem. So how many so can anybody tell what are the number of factors? Number of factors
3
are,
into
yeah, number of factors
3
would,
into 3 into 3 into 5.
yes, 3 into 3 into 3 into 5. Because we have three options for A, three options for B, three options for C, and five options for D. So we'll see that these are the number of factors.
7
Yeah,
7 power 8 is there, madam. 7 power 4, 49 power 4,
yeah.
7 power 8.
Oh, sorry. Yeah, you're right. Sorry.
It may be
Thank you.
come.
Yeah, yeah, yeah.
Yes, yes.
Yes, you're right. Thank you. It is 7 square into 4.
Okay,
So
thank
this
you.
is 7 raised to the power 8. And this should be 0 raised to the power 0 and 8. And this is 3 into 3 into 9. Thank you so much. Yeah, you're right. Nice. So this is the final answer. Now, yeah. Now we have, the next question is, we have to find the coefficient of x square in this expansion. X plus 1 by x raised to the power 20. So if we have to find the coefficient of x square. So how do we do it? There are two ways. Like there's just one way basically, but either we can directly apply the formula of binomial theorem, or we'll see how we are deriving this binomial theorem. So or we can just derive the formula of binomial theorem. So use binomial theorem directly, or second, derive formula for binomial theorem. Since we can derive formula for this binomial theorem using combinatoric method, we'll do the second thing. So what is this? So basically what we are doing, we are multiplying this term 20 times. X plus 1 by x, x plus 1 by x, till x plus 1 by x, 20. So now if we are, this basically it is 20 times. So now what we are doing basically? So if we are what is this final term? So basically from each of the bracket we are choosing one. So if we are multiplying it by 20 times, we can see, like if we open it up, it is basically from each of the bracket we are choosing one term. And how many ways we can do it? So so if we have to do it, so it is, so we have to choose 20 terms and one term from each bracket. And since there are just two terms, x and 1 by x, so if we decided what brackets are we choosing x from, then we will be fine. So basically, if there are 20 options, and first we are selecting, suppose, k brackets from which we are choosing x. If we are choosing x from we are choosing k brackets from which we are choosing x. So if we are multiplying 1 by x, we will be choosing from remaining brackets, which is 20 minus k. So we see that this term is exactly equal to this when we are summing it over. K is summing over 0 to 20. Basically, first we are choosing x from just one bracket, and so 20 choose k, xk, 1 by x to the power 20 minus k. So does everyone get how we are getting this expression?
Yeah, understood.
Okay. So now once we have this, so we just now open this up. We just solve it little more. So it is 20 choose k, and we see this will be x raised to the power k minus 20 plus k. And if we have to find if we have to find the coefficient of x square, we basically equate these two things. 2k minus 20 is equal to 2. And we'll see that k is coming out to be 11. So our answer is just 20 choose 11. Now the next question. So maybe, okay. So now we are first is we have to prove k into n choose k is equal to k into n choose k is equal to n multiplied by n minus 1 choose k minus 1. So so in question 4, these question 4 can be done using binomial identities, but we won't be doing that. We'll be finding some real problems. We'll finding some real combinatorial problems to prove this equality. So does anybody has any suggestion how can we prove the first equality? It is k multiplied by n choose k is equal to n choose n into n minus 1 choose k minus 1. So we have to do it purely using combinatorial method. So okay, so we see on LHS we have this two terms appearing n choose k multiplied by k. So can we not say that LHS is equivalent to choosing k people from group of n people and then electing a group leader. So if we wanted to, so see, n choose k means we are choosing k people from, n choose k is basically we are choosing k people from group of n people. Now we are multiplying it by k. So it is like it can be seen as from those k people we are choosing, from those k people we are electing one group leader. So we can see that LHS equivalent to this. So if we have, so if this now, so our problem is calculate the number of ways in which you can choose number of ways in which you can choose teams of k people with a team leader from group of n people. So if this is our problem, so we see one solution is through LHS. That is, first we choose k people and then elect a group leader. So can you think of solving this problem in some other way so that we get the RHS?
We can select the captain or group leader first, then we can select the remaining k minus 1 from n minus 1 remaining.
Yes, very good. So, another way is to do it, select a group leader first, and then remaining k minus 1 members. And if we do this basically turn out to be, if we are selecting a group leader first, so we are choosing, so we have basically n options for group leaders, and then we are choosing from remaining n minus 1 people k minus 1. So we see LHS and RHS both give the same, LHS and RHS both give same Both give answer to the same problem and hence they are equal. Now, once we have this, using this trick, can we find this k and choose k? First of all, convert this into a problem, combinatorial problem, this term. So we have to find this. Using the previous trick or previous identity, can we convert this term into a combinatorial problem? So we are doing n choose k and then we are doing k. Then we are multiplying it by k and k is varying from 1 to n. Can we find a combinatorial problem for this expression using the first identity that we just do? Any suggestions? Okay. So, okay. Does anybody has a suggestion? Okay. So we can see,
That,
yeah, yeah.
that will become n into 2 raised to the power n minus 1.
Okay, wait,
Because
n into 2 raised to,
2
okay,
raised to the power n minus 1.
okay. Okay, this is the answer. But what is the combinatorial problem for this?
Means all the kind of possibilities of having a group leader
Yeah,
and the rest of the team.
hmm. Yeah, you're close.
Means if we have a one
Hmm.
captain and only one member is in the team,
Hmm.
and one captain and two member in the team, all kind of possibilities are covered.
Okay. So why is it, okay, and why did you say n multiplied by, so if this is your answer, so why did you say n multiplied by 2 raised to the power n minus 1? So how does this
Because
term is solving the problem?
because
Yeah,
each of the participant we may or may not select.
okay. Yeah, yeah, that's a fine way to answer it. Yeah, good. So, or I have like it is basically similar only. So it is basic. So we can view it as a combinatorial problem, like choosing a non-empty team with a group leader, with a group leader from n people. So, so if we have to so, and now we use the previous identity. Using previous identity, so how does this using previous identity? So this is my star problem. Using previous identity, we know choosing team of k people with leader can be done in k choose and choose k ways. And therefore, if we vary over a k, if we go from 1 to n, since we are going from 1 to n, this is equivalent to choosing our problem. This number gives ways to ways for star problem. And now we want to find this, we want to simplify this expression. So our claim is that sigma k going from 1 to n, k multiplied by n choose k is n multiplied by 2 raised to the power n minus 1. So we have got a combinatorial problem. Now we have to see why it is equal to this. So as previously, RHS is equivalent to choosing a leader and then the remaining team. So we can choose leader in n ways, and now we can choose leaders in n ways. Basically, we have n options for a leader, and then if we have to choose the remaining team, basically we have to choose some people out of the remaining n minus 1 people, which can be done in 2 raised to power n minus 1 ways. So we see that this quantity is equal to this quantity. So is this fine with everyone?
Yeah, understood.
Okay, now we have a similar question. We have a similar identity. Uh, so how do we do this? 2n choose n is basically equal to our claim is this. Now can we find a problem for this? Suppose my A is P1 till P2n. So RHS is easy. Oh, sorry, LHS is easy. LHS is just choosing n elements from A, or if P1, P2, Pn are people, n people from 2n people. So LHS is easy. Now the problem is we have to express the right hand side. We have to solve this problem in such a way that we get the right hand side. So how can we do it? So you can see your right hand side is basically this: sigma k going from n. It is n choose k into n choose k, or we can further write it as sigma k going from 0 to n choose k into n choose n minus k. So we know this, I think is clear why n choose k is equal to n choose n minus 1, n minus k. So n choose k is basically choosing k people. And if you're choosing k people, you are leaving out n minus k people. So we know from this that n choose k is equal to n choose n minus k. So now if I'm writing my RHS as this, can you think of a way of solving this problem, that is choosing n elements from A such that your answer come out to be this?
We have, let's say, we have total 2n students are there in a
Yeah.
class, and out of these 2n, n are male and n are female.
Okay.
And we have to select the number of students so that total number remains n.
Hmm.
Means if we have, let's say, 10 are there, 5 are
Hmm.
male, 5 are female.
Hmm.
And we have to select the 5. If I select a 1 male, then 4 female I have to select.
Okay.
Similarly, if I have 2 and 3 like this, so because that way NCR will become NCN minus R,
Hmm.
and the net addition will become to 2 NCN.
Yeah.
Because 10C5 will become 2 NCN.
Yeah. Yes. Yes.
I hope you're getting my
Yes, yes,
point.
yes, very nice. So what is he suggesting is, suppose we have this A people. So suppose this set has like n females and n males. So basically we can partition this set into two parts. So this A is basically B, this joint union of B union C, which is, so suppose uh, assume A has n males and n females. So I'm just partitioning it as this. So suppose P1 till Pn are the n females, and Pn plus 1 till Pn plus 1 to P2n, they are n males. And our problem is choosing n people from choosing n people from 2n people in A. And how we can, so RHS is basically, step 1 is choose K females. Step 2 is choose N minus K males. And we can do this for K going from K equal to 0, 1, 2, N. So we see that this quantity becomes K going from 0 to N, and choose K, which corresponds to choosing K females, into, since these two actions are independent, into N choose N minus K, which is choosing remaining people from the category of males. So we see that N choose K is this, and we previously observed that choosing N minus K people from N people is same as choosing K people from N minus 1, N minus, from N people, because if we are choosing K people from N people, we are leaving out N minus K people. So this is just N choose K. So we have proved our identities using purely combinatorial method. So is it fine with everyone?
Yes.
Okay. So now our last problem is, we have to find number of distinct words that can be formed by letters in vowels. So we have how many? We have two G's, two O's, one L, one E, one S. And we want to use bijective counting. Okay, sorry. So the first topic that we did in the class this week was bijective counting. So we want to use this method to compute this. So basically what we want to do, solve this problem by constructing an appropriate D21 function. So I hope everyone knows what is a D21 function. So if you have a function f from A to B, a D21 function means for every B in B, order of f inverse B is equal to D. So basically D points in A go to a single point, then we say that f is a D21 function. So we want to solve this problem using a D21 function. So first of all, if all these letters were distinct, so we have how many letters? 2, 4, 5, 6, 7. 7 letters. If all these letters were distinct, so in how many ways, if all 7 letters were distinct, in how many ways, how many words do we have? How many distinct words do we have? Can anyone tell?
7 factorial.
Very good. Yeah. So I think everyone agrees. So why it is 7 factorial? Because we have 7 letters, 5, 1, 2, 3, 4, 5, 6, 7, and all were distinct. So first 7 options for the first one, 6 options for the second one, and like this. And this is just 7 factorial. So now we have that 2 letters are same. So okay. How do we do this? So since we know how to compute it for different letters, so first set A, we will consider, so I am distinguishing these G and O. So first G I am calling G1, first O I am calling O1, second O I am calling O2, and second G I am calling G2. So my A set is permutations of this this arrangement, that is G1, O1, O2, G2, L1, E1. Oh, sorry, LE we can take it as, because we have just one L, one E, and one S. So I'm saying A is my permutations of this. So can you suggest a B for this? So basically, when we are constructing a bijective count, when we are using this method of bijective counting, one of the set has to be the set that we want to calculate. So B should be, so I'm taking my B to the set that we want to calculate, to this order, to the set that we want to calculate, and which is distinct words from goggles. Okay. So any suggestion for the function? What can be the function? What can be our function? Okay. I can take my function is basically forgetful function. Basically, I forget subscripts, in G and O. This is my function. That means that G1, O1, O2, G2, LES will be sent to, forget the subscripts, it will be sent to GOOGLES. I am basically forgetting subscripts. So if I am doing this, so my claim is that it is a D21 function. That is, I can find a D. That is, in this function, every element in B has same number of pre-images. So suppose my word is this only, goggle. How many pre-images I have? This is a like if we are in this function, we are forgetting these subscripts. So basically, how many choices do we have? How many choices do we have? Sorry. How many choices do we have for the 7 places?
5 only.
5 only? How?
1 G, 1 O, and 1 L, E, and S.
We are talking about the pre-images of FN word. So basically, you need to find all such arrangement which is going to word goggles. So, so how many options do we have for the first place? What are the options for the first place? What all like if you are computing the image of goggles, in the
G1
set
and G2 can come there.
G1 and G2 can come. Very good. So we have 2 options here. And for this first here, how many options we have? For the second place? 2.
Second place, 2 again.
2 again, because O1 and O2 can come. And how many choices for the second O?
None.
1. 1 option, right? If we choose O1, it has to be O2. And if we choose O2, it has to be 1. So we have 1 option. That is, we have no option means we have to choose the one that is left. So it is basically 1. And for G, how many options? For the fourth one?
One again.
One again. And LES were already one, so we have this one option. So we can see, so what is the D? What is D? It is basically 2 factorial, 2 into 2, which is 4. Do you get it? So F inverse goggles, okay, this F inverse goggles order of this has is 4. And if we want to list it out, it is basically G1, O1, O2, G2, LES. And we change the places G2, O1, O2, G1, LES plus 2 more options. So is this fine? Why D is 4? And this will be same for every word. Every word which is formed from goggles, this will be same. Do you agree?
Yeah.
Yeah. So we see that F is a 4 to 1 function. So now if we have this, so if F is a D to 1 function and it is going from A to B, what is the order of B? In terms of order of A. So 4 elements of A are going to 1 element of B. Hello?
Yes, yes.
That's it. So we see, so it is a D, if F is a D2, so we see if F is a D to 1 function, order of B comes out to be order of A divided by D, because every element has 4 options. So if we want to count each, if we want to count 4 elements make 1 element here, right? So we see that order of B is equal to order of A by 4. And what is order of A? Order of A we know. Order of A was the set that we are already familiar with,
7 factorial.
7 factorial, and this is 7 factorial by 4. So is this fine? How we are getting the answer?
Yes.
Yes. Okay. So, so yeah, this, these were the problems. These were the problems that I selected. Now, if we can discuss, if you have any doubts from this, like any questions from this week lectures or any problem related to the topics that we have discussed.
This assignment question number 1.3, can you check whether it is?
Okay, wait. Yeah. Uh, okay. I might have. Can you dictate the question? Is it fine?
The set
Hmm.
L consists of 769 integers, none of which has a prime
Wait.
factor greater than 20.
Huh. Wait. What was the question?
I'll read slowly.
Yeah, yeah.
The set L consists of 769 integers,
Set L consists
none
of.
of which
Hmm. Yeah.
none of which has a prime factor greater than 20.
Okay. Hmm.
Prove that none of which has a prime factor greater than 20.
Okay.
Prove that
Hmm.
L has four elements,
Prove L has
four elements,
4 elements.
the product of which is equal to the
Oh,
fourth power,
4 elements which whose whose
the product
product.
of which
Whose, okay. Oh,
is
I
equal
remember
to
this question now. Product
yeah,
of this is,
equal to fourth power of an integer.
yeah, this question is correct. Yes,
Okay.
fourth power of an integer. We discussed a similar we discussed not like we discussed a similar problem
Ah,
in the last week.
so yeah, I remember.
Yeah.
See, I'm just telling you one thing, you
Hmm?
might consider it. And
Hmm.
see, if any prime power, if I took, let's say, 2 power, I write, means any of the member
Hmm.
of this family.
Hmm.
If I write 2 raised to the power x1 plus x2 plus x3 plus x4,
Hmm. Yeah.
the product of these four,
Yeah.
any of the four.
Yes.
Then x1 plus x2 plus x3 plus x4 has to be a multiple of 4 or 0?
Yeah, it has to be, basically it has to be a 0 mod 4.
0 mod 4.
Yeah.
So, and all the possibilities of each of x1, x2, x3, x4 will become 4. Either I can have a 0 remainder or 1 or 2 or 3.
Hmm. Okay.
So
3
now
to
you
6, 7.
see,
No, see, if you have a 0 remainder, 1 remainder, 2 remainder, 3 remainder, this is 3 to 6. This is 6, which is not 0 mod 4. This won't work. See, if you have a 0 remainder here, like no remainder here, 1 remainder here,
hmm,
2 remainder here, 3 remainder here, you add these
hmm.
all remainder, you get 6. So this will be 2 mod 4, not 0 mod 4. So this is not, these choices are
That's
not,
what I'm telling you. Na?
yeah.
I'm talking about in totality the summation of x1 plus
Hmm.
x2 plus x3 plus x4.
Hmm. Yeah, this won't be, but you have to, yeah. So these choices are not correct, but maybe you choose some numbers, you choose some like you. So basically, you have to make sure that it come out to be 0 mod 4. And
Hmm, hmm, hmm.
so
Okay.
okay, so like, in the last week, we solved a similar problem. Try looking at that solution and see if you can use that here.
Okay, I'll try
Hmm.
it again.
This question is correct. I solved it, I remember. This is correct.
Okay, means individually the 2 raised to the power x1 you are talking about, or
Yes.
in totality x1 plus x2 plus x3 plus x4 you're talking about.
Uh,
Because if we go with the even and odd, I'll tell you one thing.
hmm.
So in that case, the
So
product of
basically,
two,
you have to, first of all, you have to see what all the like you'll have some factors less than 20, right? Right, factor less.
these are the 8 are there. 8 are
8
there.
are there. So you want to make sure that for all of these. So basically,
Mhm,
you have a tuple of 8. So if you have 8 factors, you have
mhm,
tuple of 8 things, right? X1,
mhm,
X8. And you have
mhm,
769 tuples like this. And you have to make sure
mhm.
always you can find 4 tuples, that is, you can always find 4 tuples such that when you add the consecutive terms, when you add the one like like the coordinate wise, when you do the coordinate wise addition, you'll always get a multiple of 4 in each of those in each of these.
Coordinate wise, I didn't get you.
Yeah. So basically, see, so if you have some number this, by x1 I mean the power of 2, like all the 8
Hmm,
integers, you have this 2, 3,
hmm.
5, 7,
5,
7,
7,
and so
11,
on,
13.
11, 13.
Yeah,
So x1 refers to the x1 refers to the power of 2 in that number, x2 refers to
right,
the
right.
power of 3 in that number. So basically, you
Hmm,
have 769 tuples like this.
hmm.
769 tuples like this, and your problem is you have to show that when you, like, you can always find 4 tuples, say say x1 till x8, y1 till y8,
Hmm.
z1 till z8, and w1 till w8, such that so if you add these 4, basically you are getting 2x1 till 2x1 plus y1 to
Means 8
W1.
possibility.
Yeah,
Up to
yeah.
8 it will
So
come.
you want to guarantee that all of these coordinate wise addition. So when you add this, the number that you are getting, each number is is a multiple of 4.
But when you are talking about
Hmm.
2 raised to the power x1 plus x2, how far you are giving? You need to take only 4 there, no?
Yeah,
Because if you are going up to 8, that is a product of more than 4 numbers you are
yeah,
talking
yeah,
about.
yeah. I'm going up to 4 only. I'm just saying, yeah, I'm going up to 4 only. But
Okay, I'll
uh,
think it again.
yeah,
Maybe I'm missing.
yeah. X8 is so 8 is this number is 8 because you have 8 factors. So n is, so basically any number n here looks like 2x1, and what are the other
Right.
factors? 3,
Yeah, 3y1 like that.
no, no, 3x2, 2x1, 3x2, 5x3, 5x3, and what is the another
19,
bit?
19,
19.
19.
19 is the last factor, yeah.
Yeah.
So 19 raised to the power xa. And you have, okay. So if I also call, yes, so if I, yes, so, and your x, your, you have 769 numbers like this.
Yeah. So now
Hmm.
if you take a different number, let's say y1, y2, you
Hmm.
consider there,
Hmm.
and third is a z1, and
That.
fourth one you take
Hmm.
as a a1.
Hmm. Hmm.
So what need to be there? Then each of the 2 raised to the power x1 plus y1 plus z1 plus
Hmm.
a1 and 3
Hmm.
raised to the power x2.
Hmm.
Either it has to be 0
Hmm.
or it has to be the multiple of 4,
Yeah.
because the two
It has
numbers.
to, yeah, it has to be, yeah, it has to be either 0 or multiple of 4. But it's like,
Yeah.
yeah. So
So
you
I
basically,
think,
I think like you
see,
look
in the
at,
last problem which we discussed in the
hmm,
assignment one,
yeah,
there actually we
it was a,
even odd was
yeah,
sufficient to,
yeah,
yeah.
yeah, that was
If for
a,
the square it was okay.
yeah, that was a simpler,
But
yeah, that was a
even
simpler
if we
problem.
get the even numbers,
Hmm.
yeah, now even if we get the even numbers, it doesn't guarantee that the number will be divisible. Let's say we get the
No,
summation 10.
so even see, like see, if this, so if this is a even number, this is a even number, this is a even number, this is a even number,
Hmm.
then won't the sum be divisible by 4?
No, if we get 10, let's say,
Yeah. So see,
then
if
it
it
will
is a,
not.
yeah, if like if it is an even number, so basically you have something 2n1 plus 2n2 plus 2n3 plus 2n4, right?
Hmm.
And this is basically if you, oh, okay, n1 plus n2 plus n3 plus n4. Okay.
If
Yeah,
I
yeah.
take
That then also it
two,
won't be fine. Yeah, you're right.
if I
Hmm.
take 3 2s and 1 4, the summation is 10.
Hmm.
So in that case, the power 4, how will be getting?
Hmm. Okay.
I was just thinking,
Hmm.
maybe I'm
Hmm.
somewhere wrong or
Yeah.
something I'm
Yeah.
missing.
Okay. Yeah. I think. But if you try doing something else, you like I. Yeah, this question is fine. You can try like
Okay, question
build.
is fine.
Yeah.
Okay.
Yeah. Last date it's 10, right? Submission up. Like in
Yeah,
the
yeah,
next
yeah,
session.
I'll submit.
Yeah.
Yeah,
In we'll
I'll
discuss
submit,
then.
then we'll
We'll
discuss that.
yeah. So,
Because that 1.2 I managed to solve. It was
1.2 was the
1.3.
teens one, right? Yeah.
Yeah, yeah,
Okay.
yeah. And that I discussed with you last
Yeah,
time
yeah.
with the
So
user
did you
discussion.
use the same method there?
Yeah, yeah, that
Oh,
matter only.
okay. We don't, I don't know how that, so maybe we'll discuss both the methods in the next class then.
Right, right.
Okay. Oh,
But this, yeah, rest I will see now that. Rest all the problems we'll be discussing in the class and assignment.
yes, yes. We'll discuss the assignment problems in the next session.
Okay.
We'll discuss assignment one.
Yeah.
Okay. Any other doubt?
No, no, nothing. I was just thinking this problem only once.
Yeah, yeah. You have 4 days. Think more.
Yeah, thank you so
Oh,
much.
yeah. No problem. Do you have any other, do you have any questions, Senthil ma'am?
No, no, madam.
Oh,
But last week I didn't attend the class.
oh, oh, you,
Uh,
I have uploaded the video on YouTube and you might have got the link.
okay, madam.
Yeah, you can view it there.
Okay, then.
And also we like I'll be uploading this video with the class notes. You can view the class notes also. It is there in the same link.
Okay. Thank you,
Yeah. Okay. Yeah.
ma'am. Okay.
Okay, then I'll stop the class if there are no more doubts.
Thank you so much.
Okay, thank you. Thank you, madam. Thank you so much,
Okay.
madam.
Okay. See you in the next class.